All right. I think we want to start the first. What? Yes, that's right. So we will start today's talk, and our first speaker is Professor Bruna. He's from Kuran Institute, NYU, and his title is Addressing Computational and Statistical Gaps with Deep Networks. Thanks a lot.
Okay, thank you everyone. Good morning. So thanks for the organizers to inviting me here. It's been very nice so far. So I would like to talk to you about a couple of problems, a couple of different settings where we see it. Oh, it was turned off. Sorry. Let's see if now it's better. Is it better now? Okay. Sorry about that. Okay, so I'm going to talk to you about a couple of problems where naturally we are going to see that these architectures, these recent architectures that are so popular in machine learning, computer vision, also appear in contexts that are a bit more, I would say, mathematical, a bit more theoretical. And so let's go with it. So the first problem I would like to talk to you about is the problem of essentially that appears in many, many aspects. I guess all of you have to deal at some point with some complicated inference task. And as you all know, inference tasks can be seen as sort of optimization problems, where we might have some set of parameters here, and we want to do, let's say, maximum likelihood, for example. And so if this function is a bit complicated, how are we going to solve these things? How can we move forward? So in particular, what we have in practice is that we rely on iterative algorithms, iterative optimization algorithms, that sort of try to optimize this problem. And so in practice, we are not going to run this algorithm as infinite number of iterations, right? We are going to stop the algorithm after a while. And so what we know is that in practice, we are confronted with this trade-off between statistical accuracy, computational accuracy, and approximation accuracy. Okay, and so we know that these constraints are not independent to each other. Okay, we have this very nice, if you don't know this paper, I really recommend it to you. It's this sort of a very influential paper that sort of put the computational constraints into the game, into the mix. Okay, we have to take them into account. And so, as I said, there's all these, so how can we address which algorithms are, let's say, prime examples of the sort of setting that I am talking about. So you can have a lot of different flavors, okay? So in particular, stochastic gradient descent is one iterative algorithm to do optimization. You can do many, many variants of gradient descent, for example, average gradient descent. You can do iterative thresholding, et cetera, et cetera, et cetera. And they all have this mathematical form where an iterator at iteration n, I can obtain it as a function of what I had at previous iterations and some information that I retrieve from my model. Okay, it can be the value of the function, it can be the value of the gradient, the second order, whatever. And so the typical setting that the optimization community is thinking about are the sort of what I call asymptotic questions. For example, we might wonder, is this algorithm consistent? Okay, if I run it enough, am I going to eventually converge to the true solution? And then you can ask, well, okay, I'm happy if it converges, but I also want it to converge fast, right? So for example, you might ask how fast it converges, okay? So how fast the algorithm approaches the true solution. But these are, as you see here, you have expressions, you know, the limb, you have things that are like asymptotic. Okay, so these are all questions that involve n growing to infinity. And as I told you, it's not what we have in practice, right? In practice, n is not infinity. In practice, n is, I don't know, 100 or 50 or 60. So in that case, I'm interested in the question, given a finite computational budget, what is the best algorithm, what is the best model that approaches the solution with a given accuracy constraint? Or the dual problem for a fixed accuracy, how many iterations do I need to do? And of course here, what we will see is that now the mathematical framework completely changes, right? Because we don't have to rely on models that are known to be consistent when n grows. We need to really deal with the fact that it's non-asymptotic. Okay, so that would be the first part of the talk. And then the second part of the talk is going to involve a bit more stats. So yesterday we heard about this blessing of dimensionality. today I'm gonna, so since I thought that we had to talk about the other side, the course of dimensionality. And so how am I going to describe this course of dimensionality in my problem? So here, what I'm going to try to see is that I present you like some setting in machine learning where we have some training set. Here, this, think about this space as super high dimensional. We have some known information at some points. These are the training points. And now we try to see learning as an interpolation problem. Okay, so I give you some function. It can be the labels. It can be some regression task. So I know a function at a small subset of points, and the goal of the game in learning is to try to interpolate this function to the rest of the space, right? To fill the space by interpolating the function. Okay, so that would be my estimator. Okay, so that's a standard setup. It looks like an interpolation problem in signal processing, except that that space, it's not the 2D, it's, I don't know, 1,000,000 dimensions, right? But other than that, it looks like a standard interpolation problem. And so, of course, without assumptions, we cannot prove, we cannot say anything. So typically, what I believe, what happens in how do you call it? In learning theory, statistical learning theory, is that we try to make as little assumptions as possible on the underlying function. Okay, so particularly, in many theories, what you see is that, well, let's assume that the function that we want to estimate, f here, is just Lipschitz, okay, which means that it's stable with local perturbations. Okay, so the only thing that I control using that bound is what happens at the neighborhood of the training points. Okay, and as you know, now I can sort of rephrase the question again. If I only want to exploit this assumption, and I want to guarantee, I want to sort of have some sort of learning guarantee that my model is going to generalize well, so up to certain accuracy. How many points do I need to fill the space so that this hypothesis, this assumption is useful? Okay, and so here, that's what you see, that a very simple back-of-the-envelope calculation shows that, well, you need to fill the space with a number of points that is exponential in the input dimension. Okay, so if you want to fill the, like the unit cube in d dimensions such that the hypothesis, the Lipschitz hypothesis is useful, you have to pay an exponential price. And this is what I call the course of dimensionality, right? Because in our case, d is extraordinarily high. Okay, so I guess my point is that when we are dealing with such problems that involve images, sounds, videos, we cannot use this framework. Okay, we cannot just assume that the task that we want to estimate is Lipschitz. Okay, we need to go beyond. So how can we go beyond? So one possible tool to move beyond is to exploit the notion of invariance and the notion of stability. Okay, so we know that images are involved, they are captured, they live in the physical world, and physics have some roles, for example. I know that many problems that I care about are subject to, for example, translations, are subject to rotations. I can look at you, and then I can move a little bit, okay? And I know that this corresponds to some geometrical transformations in the input that create it's really a prior. Okay, so we have a prior in all these problems that many of the functions that we want to estimate, here the f's, have some sort of stability with respect to something that is much larger, that goes much beyond to this Lipschitz framework where I just add a little bit of additive noise. Okay, so we'll try to exploit this story. And what we'll see is that this is something that you can exploit on the supervised setting. This is something that ConfNets are very good at. And we can also exploit it in the unsupervised setting, okay, like the density estimation problem. Okay, so these are the two problems that we'll talk about today. So the first one is something that is in collaboration with Thomas Moreau, a student in École des Mines in Paris. And the second one is in collaboration with a bunch of people, mostly Stéphane Malat and Ivan Dokmanic. And I probably have no time to talk about this one, so I'm not going to talk about it now. Okay, good. So let's attack the first one first. And so we are going to focus this talk into a very specific inference problem. At the beginning, I promised you a super general framework, right? Any inference problem, you can write it as an iterative optimization algorithm, and then you can try to study that. Let's make things a bit more precise. Let's talk about sparse coding. Okay, so all of you probably have seen and used at some point some form of sparse coding. For those of you who haven't, that's the problem. Okay, so I'm going to give you a matrix, like if you want a dictionary, typically what we have is that number of columns of the dictionary is larger than the number of rows. Okay, so the dictionary is over complete. If you want, it's a frame, if you are used to harmonic analysis. And then I'm going to try to infer, okay, so given x, I'm going to try to approximate x with as few columns of the dictionary as possible. And I'm going to promote the fact that I select few components by using L1 norm, which, as you know, it's like a convex relaxation of the L0 norm. Okay, so all this is known, and statisticians love this model, especially in Stanford. So the lasso estimator was actually something that really changed and influenced a lot stats since the work of Steve Shirani. And then it has also been used in machine learning, okay, even in image processing, in signal processing. Sometimes we solve inverse problems using this model. So this model is nice because it's convex, so we can prove things, but it's not strongly convex, which means that the convergence rates of these algorithms are typically not linear. Okay, so the error doesn't decay exponentially as the number of iterations. Okay, so how do we solve this problem? There are many algorithms that solve this problem. One that I will talk about that is particularly popular is something that is this idea that is called the iterative thresholding, okay, or the proximal splitting idea. Okay, it's an idea that is pretty old. It dates from the 70s. And the idea is the following, is that we look at our function that we want to optimize, and what we're going to do is we are going to do some form of Taylor development. Okay, we are going to do a first-order approximation of this function around our current estimate. And then rather than optimizing the original function, we are going to try to optimize the upper bound. Okay, and we can construct the upper bound because the function is convex, and the upper bound can be optimized analytically. Okay, can be solved completely. Okay, so that's the principle of proximal splitting, and it results on this algorithm that is super famous. Okay, that gives you this following rule. Okay, so I will update my new estimate at iteration n as by applying this sort of complicated expression, but it's not so complicated because that's linear, that's like a constant term, and this is an operator. Okay, that's an operator that's called a soft thresholding. Okay, it's like a shrinkage term that you apply coordinate per coordinate. And then you can prove, you can have this guarantee, right? That if I follow this rule, then eventually I will converge to the solution, okay? With a speed that is not great, okay? But in practice, people use it, and you can accelerate it with something that is called an ester of momentum, okay? But this is not part of this talk. Okay, so what is the relation between this and deep networks? Okay, so that's something that I promised at the title of the talk. So if you look at these operations here, what am I doing? I'm doing something repeatedly, where every step is going to involve some linear operation on the previous step plus some bias. Okay, so that's like an affine operator that is followed by a nonlinearity. Okay, but this nonlinearity is pointwise. Okay, it applies coordinate by coordinate. So this, for those of you who have manipulated deep networks, should sound extremely familiar, right? Because all the operations I'm doing are natural. So this is something that people know and like. Okay, so this is a known territory. So indeed, you can write the diagram of this operator as a recursive infinite deep network, where I will alternate between a linear operation, that is the affine operation that I told you about, and a soft shrinkage. Okay? So that's just a diagram. And this, if I plug this and I put infinite layers, I get exactly the lasso estimator. So now what is the idea that Carol Gregor and Jan LeCun proposed? Well, of course, we are not going to run this algorithm for infinite number of layers, right? We are going to run it for, 100 steps. Okay, that's what you can afford in your CPU. So what you do is that you say, well, I'm going to run it for 100 steps. Okay, so now I have this thing here. But now I have no guarantee here a priori, right? I have an intermediate solution of an algorithm. So now the main insight was to say, well, maybe we can optimize the parameters of this network such that the output, so this estimator, is optimizing my inference task that I care about. Okay, in our case, this reconstruction error and the sparsity. Okay, so that's what this Lista, like the learn iterative thresholding model is doing, right? It's just unrolling, freezing the number of layers, and then training everything end to end. Okay, so now we can train these layers. We can adapt the linear operators here so that the corresponding finite iteration model is optimizing the task that we care about. Okay? And how do we optimize these parameters? By just gradient descent. Okay? Any questions? That's clear? Okay. Okay, so now let's try to understand why this works. Okay, this was actually very successful. Okay, and actually it's like an example of a deep architecture that sort of enters the territory of a very famous and respected algorithm, and then suddenly shows that, well, in the non-asymptotic regime, maybe there are better choices than this linear term and this affine term. Okay, that's the whole point. Okay, so maybe I can modify these linear terms such that if I run it for m steps, I can go faster. I can go faster to the solution. Okay, that's the whole point. So let's try to understand a little bit why this is possible, when is it possible, and what is the underlying mathematics. Okay, what is the underlying reasons why this can happen. So let's go a little bit into the principle of the proximal splitting. Okay, so why does the proximal splitting work? Okay, what is the principle that allows me to say I can approach a solution by applying this affine transformation and then this pointwise shrinkage? So the main power of this method is the separability. Okay, that I can able to break the problem that is n-dimensional into a bunch of optimization problems that are separable. Okay, that operate at each coordinate independently. Okay, and why is that? Well, the reason why we have this property is because, as you know, the L1 norm is separable. Okay, so the L1 norm, you can express it as the sum of absolute values of each coordinate. Okay, so I can express it as a sum of stuff that involve things at each coordinate. And now, of course, the first term, okay, like the L2 reconstruction term, a priori is not separable. Okay, if the dictionary is not aligned with the canonical axis, it's not going to be a separable term. But if I find an upper bound, a surrogate that is separable, then I'm in business. Okay, so that's the main principle of the proximal splitting. Okay, so the idea is that you find a surrogate term, okay, something that is an upper bound, a controlled upper bound of the function that has the property that is written as a separable function. Okay, so this is a diagonal term in the standard proximal splitting algorithm. Okay, so now I can minimize this stuff. Okay, because everything is separable. Okay, so I can operate coordinate by coordinate, and I get the proximal splitting algorithm. Okay, that's the principle. Okay, so now let's consider a unitary matrix. Okay, let's consider a rotation. Okay, it's basically the same principle as before, but rather than applying this surrogate at the z and the previous point, I'm going to rotate the problem. Okay, I'm going to rotate the space and then apply the surrogate. Okay, it's like a sort of changing the point of view. Okay, and you do a rotation. So the main observation that we have is that this is still a surrogate that can be explicitly minimized. Okay, and it's very easy. It's one line. You can do it in the back of the envelope. But applying the rotation here doesn't change the property that you can solve it in one step. Okay, and so now you have a more general principle of constructing a surrogate and optimizing it explicitly. But of course, the question is, well, how do you choose this matrix, right? In the standard algorithm, this matrix is the identity. So how can we choose it in practice? Okay, so for this, we are going to introduce another piece, a small piece of notation, that is something that I call how the L1 norm, how the L1 ball is perturbed by the rotation. Okay, so think about the rotation as like a sort of evil rotation. Is one that is going to completely change the L1 norm. Okay, so think about a rotation that sends a vector that is like, in the canonical direction into a vector that is very, very far away from the principal axis. Then there are chances that this thing is very large. Okay, and so what we have is a sort of a quantity that measures how invariant the L1, so how invariant the operator is with respect to the L1 norm. Okay, so that's the first error term. And the second one is the residual, as before. Okay? And so what we see is that if we are able to construct pairs of rotations and diagonal matrices such that the corresponding residual is positive definite, then we can completely control, okay, how far we are from the final solution. Okay, so what we see here is that the error that we produce now depends on how well we have been able to factorize the dictionary matrix and how how much the L1 ball changes with respect to the corresponding rotation. Okay, so what we see here is that we have a trade-off between two properties. Okay, we want to find a factorization that has a small residual. Okay, so if you think about the standard rotation, so that's the, sorry, I forgot to tell you what this is. This is the gram matrix of the dictionary. Okay, it's like a positive definite symmetric kernel. So if you could find, like, let's say the SVD of this, you would have a perfect factorization, right? If this is the SVD of this, that would be 0. Okay, so that's good. But then that would be maybe large. Okay? And if you choose the identity on the other extreme, if you choose here to be this the identity and this a diagonal matrix, that will be very small, but that will be very large. Okay, so what you see here is two things at play. Okay, so you want to factorize, but trying to find rotations that are not too far, okay, from a permutation matrix. That's what we are proposing here. Okay, and so this is I don't want to bother you with this, but you can see that if you plug in these two properties into the, you can plug in these properties into a guarantee, into a bound of the corresponding algorithm. Okay, so if I have the modified ISTA, where at every step I choose this factorization, then you can control the error. Okay, and so what you see is that we have a bound that, in a sense, depends on two things, right? And mostly depends on how well we are able to find these rotations that sort of leave the L1 ball almost invariant while having a small residual. Okay, so how does this compare with the baseline? Okay, with the choice where we don't bother about finding this rotation, and we just use the standard unitary, like the standard identity. And so what we see is that we are going to produce a better bound, okay, as long as this inequality is satisfied. Okay, so this is actually the standard, this is the norm of the gram matrix. Okay, so that's the sort of in a sense, the size of the dictionary, if you want. And then we have two terms here, the residual, and then something that depends on the, like, let's say the invariance with respect to the sparsing. And what you see is that there's something that you can sort of refer to a phase transition. Okay, so it depends where in the algorithm you are. Okay, if you are at the beginning of the algorithm, what you have is that you are far from the solution. So this term is large. So what it means is that if this term is large, you can afford to create some error with respect to the L1 ball. Okay, you can afford to make this term a bit large. Okay, because then that would allow you to make this term small. But then at some point, once you get closer and closer to the solution, this term, okay, becomes very small. Okay, so you start to pay a big price by applying rotations that are far from the identity. Okay, so here, what this suggests is there's a phase transition where at the beginning of the algorithm, we can accelerate very much by finding these rotations that sort of make this term small. But then at some point, the gains are going to be like a diminishing returns, right? At some point, we really need to resort to the standard algorithm. So this is what we observe. Okay, so numerically, this is what the algorithm does in practice. Okay, so at the beginning, you get very important gains at the beginning of the algorithm, and then eventually the rate sort of approaches that of the standard algorithms. Okay, and this is something that we have even for dictionaries that are completely unstructured, and also for dictionaries that are structured. Okay, so this is dictionaries that we used based on wavelets. Okay, so just to wrap up this first part of the talk, what I presented you is a very simple problem, okay, like a sparse coding problem, where already you can see that once you change the problem into, okay, tell me for a fixed number of computational budget, what is the best operator that sort of estimates the true, the underlying sparse codes. This is a problem that, in a sense, is of a completely different flavor from the standard problems that we study in optimization theory. And what we have tried to see is that, well, maybe you can sort of start to use the language of neural networks, because the resulting estimator is going to have the architecture of a neural network, and that somehow you can relate the choice of the neural network parameters with actually fundamental geometrical properties of the problem. Okay? In that case, we try to relate the weights of the neural network with some form of factorization of the gram matrix that respect the certain properties. Okay? But there are still a number of things that we don't really understand. Okay? So the first one is that we are currently being able only to match the result of the original neural network algorithm. We haven't still figured out a way how to actually improve it, make it a bit more robust. Okay, so that's something that we are currently working on. And so, and the other thing, of course, is that I showed you sufficient conditions. Okay, so if the graph matrix can be factorized, then we can accelerate. We don't know if the converse is true. Okay, so that's something that we are still leaving it open. Okay, so that's for the first part. And so now I'm going to sort of change a different setting. Okay, so I'll try to present you another setup, okay, a bit more similar to, closer to some aspects in machine learning, where I also I will try to present that neural networks, in that particular case, convolutional neural networks, appear very naturally. Okay, they appear very naturally as very powerful, very interesting mathematical objects to solve a particular statistical task. So I'm going to try to motivate it by a very, a very sort of relatively standard setup, which is inverse linear problem. Okay, so I hope that this is not going to be too boring. So let's assume the following problem. We have some observations y, and we want to infer, we want to estimate x. Okay, x, the measurements and the signal and the measurements are related via linear operator gamma that is singular. Okay, so that's a super standard setting in signal processing. Okay, and we can add some noise here if you want, additive noise. And so there are many problems that that engineers care about that can be studied using that framework. Think about super resolution or in painting, okay, or sort of very nasty inverse problems, okay, where you cannot just invert gamma and be happy with it. Okay, so these are very ill-posed inverse problems. So probably you have seen a lot of papers, okay, a lot of even in textbooks, that what is the standard way to think about these problems? What is the standard class of estimators for this problem? Is to try to follow what I call the standard regularization route. Okay, so you are going to introduce some prior on the solution, and you want to try to find a point that agrees with the measurements and is not too bad according to my prior. Okay, so typically we use a convex regularizer. Think about, like, I don't know, the total variation norm. You can think about the L1 norm in some dictionary, you name it. Okay, if you use here some sort of Tikhonov regularization, then you have something that is even more standard. Okay? And so my question is, well, how appropriate is this formulation, is this route to deal with, I would say, challenging inverse problems that involve images? Okay? And how can you leverage training data here? Okay, so how can you address these two questions? Okay, so of course, some people, when they look at this, okay, they like to think about some sort of log likelihood or minus log likelihood that is being optimized. Okay, so there are always this dual vision. Okay, so you can always think about this thing in terms of optimizing, okay, doing some sort of maximum likelihood estimation. So in that case, the maximum likelihood estimation correspond to finding, the mode of this distribution. Okay, so we have a term that is sort of relating the data reconstruction term, and then we have some prior. Okay, but the point is that this has a limit. Okay, so assume that I give you two solutions, x1, x2, that they have the same density. Okay, that they have the same sort of likelihood according to that model. Okay, since this minus log likelihood is convex. Okay, I told you here, this is convex, if this can be convex, then what happens is that if I give you 2 points that have the same likelihood, if I look at any point that is in the line that goes from one to the other, it's going to have a likelihood that is at least as large, right? Okay, that's the principle of convexity. So is this something that is appropriate in images? So think about it. Okay, so let's think about a simple model. Okay, so here are my observations. Okay, and think about like a super resolution problem, like a blurring problem. Okay, so here I have my observations, and I give you two possible signals that might explain this bump. Okay, so think that the inverse problem here is taking a signal and then blurring it. Okay, so these two things seem equally likely, perhaps to have produced this observation. But now, according to this simple equation, what it tells me is that any linear combination of two bumps is more likely, according to that model. And what happens when you have a signal that is very sharp and you start averaging with neighbors that are a bit translated? You blur it, right? The high frequency is not protected by this model. Okay, so in a sense, we have something here that is quite fundamental limitation of a convex formulation of the problem. We cannot capture high frequencies with a convex problem, okay? Because the convex problems are, by definition, gonna assign better likelihood to locally averaged solutions, okay? And this is something that it has many, many names. Some people instead, they call it the regression to the mean, okay? When you try to find solutions by optimizing a convex problem, you are essentially finding the mean of some posterior distribution, right? And if this posterior distribution has one mode, it's gonna essentially go for the mean, okay? So how can we go beyond this thing? Okay, so here's one possible route, okay, that sort of connects with the previous thing that I discussed. So we can try to change a little bit the gears and say, well, let's try to do modeling of images by sort of considering more like a generic vector of sufficient statistics. Okay, so what do I mean by that? Is I told you before that sort of a prior in an inverse problem or a generative model, like a density model, are sort of equivalent, right? It's just an equivalent formulation. So we can try to look for like probability models that have sufficient statistics given by some feature vector. Okay, so think about this feature vector, something that can be very generic. Okay, of course, we will end up with feature vectors that are conv nets, that are convolutional neural networks, but just bear with me in this general setting. Okay, so what are the properties of this model, okay, that depends on the sufficient statistics? We can maybe encode prior knowledge. Okay, so let's say if the sufficient statistics sort of have a dimensionality that is much lower than the original point, then we might learn parameters in a much smaller dimensional space. That's good, okay? That could be one possible advantage. But then what is the other major advantage? Is that now I told you that we have maybe some prior, okay? So all these models, they are stable with respect to geometrical transformations. For example, if I translate X, I would like the density to not change too much, okay? So that's a very natural prior. So this is something that I can encode very naturally in sufficient statistics that themselves are stable, okay? In other words, if I have sufficient statistics that are stable to transformations, and the parameter, the learning is smooth, then I transfer this stability to my model, to my generative model, okay? So one example that is very famous, okay, that sort of follows this route is you can think about the exponential family, okay? So if I have an exponential family that is given by these sufficient statistics, right, I get like a class of models. And of course, this has very nice properties. You can think this as in terms of the maximum entropy. Okay, so this model is the distribution that has maximum entropy with the constraint that the expectation under my model of these sufficient statistics matches the expectation of the data, or like the empirical expectation of the data with respect to the same sufficient statistics. But for those of you who have manipulated these models, you would be a bit scared, right? Because here there are two challenges, right? The first challenge is that, well, in this parametric model, how can I adjust these parameters? Okay? How can you fit the parameters of this model to your data? Complicated problem. How can you sample from this distribution? Okay, so here, as you see, this is a very general, this is a Gibbs distribution. Okay, so these two problems have to be addressed via very expensive inference and sampling. Okay, so they are very interesting and beautiful algorithms to do that, but we have to be ready to pay a very expensive price. Okay, so now we can sort of connect it. Okay, we can sort of try to find an alternative route. Okay, so that's something that will lead us to a model that is easier to infer, is easier to do inference and sampling. Okay, and so think about features. Okay, so can we find features such that when I send any distribution, okay, I have an input process X, the transform features are going to have a well-behaved distribution. For example, Gaussian. Okay, so can we find features that Gaussianize my distribution. Okay? So now we can use the maximum entropy principle, but in a different flavor. Okay? So now we could say, well, now I can define my model as being the maximum entropy distribution that has the same distribution in the feature space. Okay? And so what are the advantages of this model with respect to the standard maximum entropy in the exponential family? It's just that now, if we have a very simple property, okay, so if we just assume that our features are sort of preserving the norm, like think about this as sort of the nonlinear equivalent of a frame, okay, so these are like the frame bounds, then the corresponding maximum entropy distribution has a very nice form, okay, and this is something that for those of you who have some exposure to statistical physics, now you can start to see where I'm going, right? So this, what I'm going to see is that I can sort of use the what's called the microcanonical ensembles. Okay, so the maximum entropy distribution that is defined by these constraints is obtained very easily, right? I just sample from a distribution that is known. Okay, that's the thing that I'm assuming, and then the maximum entropy distribution constrained to be to have z is actually the uniform measure on the anti-images. Okay? So this is something that is referred as in statistical physics as the microcanonical ensemble. Okay? The microcanonical ensemble is the set of points that agree with a certain feature vector. Okay. So of course, I'm not telling you here so far how should I choose the sufficient statistics. Okay? So these are very general statements, right? But then how should we choose the sufficient statistics? So what are the properties that we want in that setup? Okay, so we would like maybe to have properties that are good at transforming very complicated distributions into something that is well behaved. For example, Gaussian. Okay? So what is the mechanism to construct a Gaussian distribution? There are many, right? But the one that I prefer is the central limit theorem. Okay, so if I can somehow guarantee that my features satisfy a central limit theorem, then I'm very happy. Okay? Because I can sort of use the previous slide. Okay? And what you see is that in order to ensure that you have this central limit theorem, you have to control the total variance of your representation. Okay? You will see that this is something that becomes critical. And then the other property that this model requires is that, as you know, the sufficient statistics, they need to match with the smoothness of the density, right? I mean, the microcanonical ensembles, okay? So this model, what it means is that if the sufficient statistic doesn't change, the density doesn't change. Okay, so I need to have some form of smoothness with respect to that level sets. And in particular, what we see here is that the larger the level sets are, the harder this constraint is going to be, right? Because if I impose that the original density is smooth over a super large level set, well, it's going to be much harder to impose than if I have level sets that are very small. Okay? And so here, what you see is that it's also important to, on the class of models distributions that we care about, we have small level sets. And this, what we see is that in high dimensions, a tool to control the size of the level sets is the sparsity. Okay? We will see these two properties. Okay. So now, how can we apply these general things to images? Okay, so as I told you, we need features that are sort of stable, okay, with respect to the sort of the intrinsic variability of this level of the distribution. Okay, so think about a model now that I call the geometric variability. That what it's going to do is that rather than having like additive noise to my images, to my pixels, it's going to add noise to the position of the pixels. Okay, so it's going to take u here, that's the position of the pixel, and it's going to move it. Okay, so with this, we can sort of that's a very like, of course here we are doing a bit more than that, but that's just to illustrate what the sort of thing that we can model. Okay, so with that geometric noise, okay, we are moving things around. We can model things that are very appropriate when we have to deal with images, right? You can move things. Okay, you can even move around Italian art. I don't know exactly what is the period that this is spanning, but you can sort of, you can visit the manifold of images if you want. But of course, here we are adding noise. So what is the mathematical version of? So we need to define a couple of things. So we need to define what is the corresponding variance of the noise. Okay, so that's a very form of geometrical noise. So we have to sort of design a deformation cost. Okay, so the deformation cost, we can measure it using different tools. In particular, we can say, well, we are going to pay a price by measuring to the extent by which the pixels move. That's this term here. And then the extent by which the pixels are deformed. Okay, so it's different to move everything in a rigid way, where this thing would be large, but this thing would be 0, than starting to stretch and deform stuff. Okay, so that's the two terms that appear here quite naturally. And with this, we can model many things. Okay, so we can model change point of view. We can apply this for speech, because we can model frequency transpositions. And in a sense, it's something that is quite general. Okay, so it's, and we can, so changes of point of view, and etc. Okay, so how can we deal with that model of deformation? So first, we can try to ask, is there a linear, are there some linear features that are consistent with this noise model? Okay, so in a sense, we are looking for a linear operator A that if I apply noise, I'm going to not change too much, okay, that they are stable with respect to this noise variable. So in a sense, the only linear operator that is stable with respect to this form of noise is the local averaging, okay, it's the blurring. Okay, and it's very easy to see that it's the only thing that we can do. So this is not very exciting, right? And it's actually pretty dangerous. Because if I blur things, I lose the ability to do machine learning, right? I lose the ability to recognize. Okay, so here, the linear operator is completely destroying information. Okay, so a linear operator is not sufficient for addressing this problem. Okay, we need to complete the linear operator with something that is nonlinear. Okay, so the first thing is that, well, let's try to find the information that is lost. Okay, the information that is lost by the blurring, as I told you before, it's mostly concentrated in the high-frequency information. The high-frequency information is the enemy here. Okay, it's the one that is very unstable with respect to the variability that we see. So the first thing we try to do is capture this high-frequency information with a filter bank. Okay, so in a sense, we have this low-pass filter that is like a convolution with a kernel that is low-pass. So now we complete this low-pass filter with a family of filters that might be localized at different scales and different orientations. Okay, and this is something that you might have been using before. It's like a wavelet filter bank. Okay, and so wavelets are non-unique. You can choose different families. But one of the things that that is important in the theory, we won't have time to talk about the details here. But I told you here that the low-pass filter is locally invariant to deformations, right? It kills the deformations. So the next best thing that you can ask in a linear operator is that it's sort of covariant to deformations, okay? In the sense that if I apply a deformation and I transform, then I can recover the same thing if first I apply the transformation and then I deform. But of course, this is still a linear model, so we need to apply a nonlinearity here. Okay, so here what we can see is that we can apply a nonlinearity that is pointwise, okay? And in particular, if we apply the convex modulus, we preserve the energy, and we can see that it preserves, okay, so it commutes with respect to this geometric noise. Okay, and so now we can define, okay, with these three ingredients, we can define a very simple but quite powerful convolutional neural network. Okay, so we start with our signal f. We apply these low-pass filters. Okay, so this is already coefficients that are good, and then we compute the residuals, okay, by computing these wavelet coefficients. These wavelet coefficients are not stable, so we send them through this pointwise nonlinearity. Okay, but now we are here. We have signals that have already been demodulated, okay, with the modulus. So now we can reapply the same thing again. Okay, so we can apply the same thing again and again and again. And what we see here is that we have a cascade of operators that are all contractive, okay? And they are essentially involving convolutions and pointwise nonlinearities. Okay, so this is a very particular class of convolutional neural networks. And so just to give you a very brief idea, a very simple, a very fast idea of what these things are computing. Okay, so as you might be familiar with SIFT, which are a class of local feature extractors for images. So this, in a sense, is sort of related to the first layer of the transform. Okay, so here we have two images, okay, two patches that have exactly the same first layer coefficients. Okay, so they have exactly the same energy along each scale and orientation. But you see that they are very different. Okay, these patches are very different. So where is the difference coming from? The difference coming that is that they have the same energy across each scale and orientation, but the way the energy is distributed in space is very different. Okay? And so what you see here is that this difference appears very naturally in the second layer of the processing. Okay? So we are able to capture geometric things by looking at this, by looking at the second layer of the transform. And similarly, if you look at like a stationary texture, stationary process, you can actually construct two processes that have exactly the same power spectrum. Okay, so they have exactly the same correlation structure. And so you might want to understand, okay, to see where, if you apply this scattering transform to understand or to study stationary processes, you can see that by looking at the layers, at the information that comes after the second layer, we are able to capture higher domain information. Okay, in the sense that if we only look at correlations, we cannot distinguish these two things. But if we look at our scattering layers, scattering coefficients, we are able to discriminate, okay, between these two processes because they have different higher domain information. Okay, so here, in the sense, the nonlinearities are helping us to get to this higher domain information. Okay, so we have this provable stability and provable control of the variance. Okay, so these are the case with respect to the geometric noise. This is the control with respect to the variance that I told you about. And now I'm going to just conclude with a couple of applications of this. Okay, I'm going to skip this one because I don't have time. Well, yeah. Okay, so here what you see is that using this model as a generative model, what you can see is that we are able to sort of capture very simple geometric structure. Okay, so these are original textures. We estimate these parameters of this Gaussian model that I told you before, and we sample. Okay, what you see here is that with very, very small number of coefficients, we are able to recover very important geometrical properties. Okay, so we are able to recover some geometry that you cannot do with the Gaussian model. You can do better by making the ConvNet larger. Okay, so this is work by some of my colleagues in Germany. Okay, so you can even reconstruct meat, okay, and landscape, okay, by sort of making the number of features larger and larger. And okay, if I have 1 minute, yeah. Okay, so if I have 1 minute, I will just wrap the talk with another application, okay, where, in a sense, we also put these ideas to sort of relate it to a very standard inverse problem. Okay, so this is a super resolution problem. So here the task is to go from, a low resolution image to a high resolution image, and we can look at this problem using different techniques. In particular, the one that sort of get the state of the art until recently is to sort of brute force the problem, okay? Look for a very complicated nonlinear regressor, and then try to optimize this cost. But from what I told you before, that's a metric that is not very appropriate for this problem, okay? In the sense that it's not very stable with respect to geometrical transformations. So something that we can do is to look at solve this statistical problem, but using a better metric, okay? So how can we do that? We can look at their features, we can compute the scattering coefficients, we can look at the target, we can compute the scattering coefficients, and now we can try to solve the estimation problem in that domain. Okay? In other words, we are changing the metric. Okay? We are trying to get a metric that is stable to deformations. And in particular, we can even use this thing to be a linear operator. Okay? So it's just solving the pseudo-inverse here. Okay? So I will just finish with showing you some results. Okay? So here are some examples of super resolution, and here, like that's the state of the art. Okay, so that's using a very expensive convolutional neural network that is trained by optimizing PSNR. This is what we get with this very simple linear operator. Okay, and so you can see that although you can agree or you can disagree, we are able to sort of recover high frequency information with much less pain. Here we are just doing a linear operator. Okay, so all the nonlinearity is encoded in these sufficient statistics that are built to be stable to deformation. Okay? And even we are able to recover texture information that is very hard to recover if you just try to regress in the original domain. And with that, and with something that we are currently working to apply at the different geometric models, in particular point processes. Okay, so with this I will wrap up. So what I showed in the second part is that by using these sort of generic features that are sort of have the architecture of a convolutional neural network, we can maybe beat the course of dimensionality in this class of problems. And we can use this in both supervised learning, as we have seen in the media or during all these years, but also in the unsupervised learning. And still, we have a lot of stuff to do to understand what's going on. We need more people who is interested in theory to help us understand what's going on. But we have some ideas on what are the things that are important in these architectures. There are some things, of course, the role of learning is still a big mathematical open question for me. So with that, I will just thank you very much and open for questions.
Looking at the declarations you were able to do, can you say anything about classifying images into homotopic groups?
The homotopic groups is the, what is?
Images that are equivalent under the nice transformation.
Yes. So yeah. So it's something that I didn't really expand here, but you can actually, as long as the group is compact and you can define a wavelet representation on the group, then you can actually prove that your representation is invariant with respect to the group. So two images that are related with a group action, they are going to be mapped to the same point. So that's something that we have applied for translation groups and then roto-translation groups, which include some rotation. But in images, the one that we are not really able to capture well is as long as you have some dilation. Because in that case, the group is non-compact, and it's not easy to define a wavelet transform in this non-compact group. But so I don't know exactly the group that you had in mind, but we can discuss maybe offline.